laws and applications. So we did some problems on the application of Newton's laws. We did this active machine, which is like a mass-produced system. So we have to practice n number of problems based on these lots of such situations, including friction, non-including friction, and so on, in different kinds of configurations, horizontal surfaces, inclined planes, and all. Okay. So what I plan to do today is to go through some applications on the conservation of momentum. So we had talked about a couple of classes back. So we talked about Newton's laws and the conservation of momentum as well, linear momentum. We have taken up problems on Newton's laws, and today we will be taking up problems on the conservation of momentum. Okay, so conservation of momentum. Just to remind you of the statement of the law of conservation of momentum. So from Newton's second law, we have force to be the rate of change of momentum. So if the net external force F acting on the system is 0, then dPdV would be 0. If F equals 0, this is like the external force at 0. That would imply that P is constant. So essentially that's the statement. That if the net external force acting on a system of particles, be it two colliding systems, be it a number of particles colliding within each other, right, through some force of attraction. In such a situation, if it's only happening due to the fact that they're interacting within themselves, then the linear momentum of that system would always be constant. So, at any point of time, so if you take into account the situation before the collision has taken place and the situation, that is the final momentum, after the collision has taken place, they should be the same. Okay. And if you remember, we had been talking about, while discussing about collisions, there are multiple types that one could consider. One is a special type called the elastic type. What happens in an elastic type, apart from the fact that momentum is conserved, is additionally kinetic energy, initially and finally, pre-collision and post-collision, they are conserved, which doesn't happen in the case of inelastic collisions. And then there is this another extreme case, the perfectly inelastic collision, in which basically the two colliding objects, they kind of stick together and share a common velocity after the collision has taken place. So we'll do this kind of an example first, where it's a perfectly inelastic collision. And this is something called the ballistic pendulum. Okay. So the situation is something like this. Imagine a hanging wedge. A wedge is just a massive wooden block. Okay. So this is a hanging wedge. This is initially at rest. This is at rest. And let's say the mass of the wedge is m suffix w. And the bullet with a certain velocity, vb, let's say, is about to strike this block. And the mass of the bullet is also given to be mv. Okay. And after the collision has taken place, the bullet gets embedded into the block. And as a result, what happens is dashed lines, the net system, that is inclusive the wedge and the bullet, they kind of reach a certain height. Let's say the maximum height that it goes up to, with reference to, let's say, the middle of the block, a line passing through the middle of the block, is h. So we have to find out what this h is. H is the maximum height attained by the block along with the bullet embedded. So this would be a situation which we will say is a situation of perfectly inelastic collision. Because the two colliding masses, they have stuck together and then maintain the common velocity. Okay, so what should be the approach? How should one go about finding out h? First of all, is the statement of the problem clear? Do you want me to repeat the problem again? It's simple as that. A block, a hanging block, I call it a wedge, is at rest initially, right? And there is a bullet about to approach it with a velocity dv and having a mass mv. And after the collision has taken place, so maybe I should write mv plus mw here. After the collision has taken place, the bullet gets embedded into it, and the combined system reaches the maximum height of h, and we have to find out this h. The question mark is how much? In terms of whatever the parameters are. So I'm not providing you with any numbers. We will do everything in terms of the parameters. Okay, so what's the approach? Kinetic energy should be exactly good. So first of all, one needs to find out the common velocity of the block and the wedge system. Once the bullet has hit the block, what would that do? That would give you the kinetic energy or the total energy, the total mechanical energy when the bullet has struck the wedge. Now this complete mechanical energy, which is essentially kinetic here, would get converted into gravitational potential energy at the maximum height. So that's the line of thought. That once you find out the velocity here of the combined system, with that velocity you can find out the kinetic energy and hence equate that to mgh, which is the gravitational potential. Okay, so in order to find out the velocity, the combined velocity, you just have to conserve the momentum of the initial and the final. So, initial momentum is what? It's pi. So, p is the common letter that we use for linear momentum. I stands for initial. So that would just be mv times v. The wedge was at rest to begin with, so no momentum associated. So what is the final one? Final in the sense after it is just taken off. That's the final one.
mb plus m
That's pf equals mv
plus mw
plus mw times
common velocity.
or if you like pf. So just equate these two together. So now apply from, or let's say just from, conservation of momentum. You just equate pi to pf and get v pf equal to mv times dv divided by mv plus v plus v. All good? Okay. So, this velocity will be associated with the kinetic energy of the block bullet system. So now, the kinetic energy would be equal to half mv plus mw times this vf square. This piece. potential energy once it reaches the maximum height would be equal to the potential energy. So this was the conservation of momentum part. And now we are equating, now we are essentially using the conservation of mechanical energy. I wouldn't say kinetic energy now, because we are not dealing with a case of elastic potential. So it's mechanical energy. Remember, mechanical energy has two components: the potential and the kinetic. Okay, so it's mv plus mw times g times h. Mg is simple as that. So just equate these two, and you get, so equate from conservation. You get
half E square by G.
equals
Half E square by G.
v square
2G.
because all the masses will drop off once you equate this with this with this mass. So just substitute Vf to be this. So it would be mv over mv plus mw square
VB square by 2G.
1 over 2g and times vv square. So that should be the maximum height reached by the combined block figures. Is this dash kind of obstructing you? This looks good, but we're actually sitting here. Okay. Any questions here? Okay. So this is something called the ballistic pendulum. There are some applicational details to it. I need to check that out. Does anyone know why ballistic pendulums are kind of useful? I used to know this. I'll get back to you once I go through it myself. There are some military or some applications involved with ballistic pendulums. Okay. So let's move on to another problem. This is again a very common conservation of momentum problem, which is called problem of recoil, or this phenomena of recoil. You know what that is?
Bullet.
Right. It's usually when we all have tried this at some point. You usually have this air gun, this melas होता है ना, मेला होता है, and you have these bullets and the balloon. Once you fire the bullet from the air gun, you feel a back push. Why is that? That's essentially the recoil. And that recoil basically happens because of the conservation of momentum. So it's a situation like this. You have okay. Imagine this to be a rifle. Not a good one. Looks more like a gunpowder actually. We have this. Trigger makes a difference with the gun. Anyways, so this is a rifle. Okay, and bullets are into the rifle, but when you fire bullet, okay, now let's say of mass mv and vb. Velocity dv is ejected out of the nozzle of the gun of the rifle. In the process, what happens is the rifle has a recoil, and let's say the recoil velocity is vr. So we have to find out how much vr is given the mass of the rifle is mr. So what could that be? So everything was at rest to begin with. So what's the initial momentum?
Zero.
Just zero. Because everything was at rest before you fire. Right? So the initial momentum, Ci, is just zero. Now, what's the final momentum after you have fired the bullet?
mr minus mb.
Right? mv times bv. Add that to mr times br. Now,
Sir, mr
you might
minus
be
mb.
tempted to include a minus sign due to the recoil, which is opposite that of the velocity. But even if you do not do that, and you equate the two, you will see that a minus sign automatically emerges out of the calculation. So the next step is the obvious one. You equate the initial and the final momentum.
Sir, after the bullet is fired out, the mass of rifle reduces by the mass of bullet.
Yes, but yeah, you're right. I mean, this ideally saying is the rifle is such massive as compared to the bullet that mr minus mb doesn't make much of a difference. Or the other way to modify it is this mass that I'm talking about of the rifle is already minus the mass of the ejected bullet. Okay. So that would tell you that 0 equals mv times bv plus mr times dr. So that would tell you that vr is equal to minus mv times bv divided by
mr.
So that would be the recoil velocity of the rifle. And you already see that a minus sign has appeared. Although we haven't considered separately the direction of the velocity, so it automatically emerges out of the calculation. Had you already considered minus, then also you would have been right, because you have already assigned the right direction. Then in the calculation it won't appear on this, because you already have a minus sign. Okay, so now let me ask you a question. This is pretty straightforward. So, as you can see, the mass of the rifle being larger, or pretty much larger, than the mass of the bullet. So this recoil speed is kind of low. Although you feel it, it's kind of low. Now, this situation should also happen if you project a particle up from the surface of the earth. Then the earth should actually also recoil, because imagine the similar situation. You project a particle up, then you would also expect, due to the conservation of momentum, the earth should also recoil. But could we actually sense that? Why don't we sense it? Exactly. Because of the huge difference of mass between the projected particle from the earth and the difference, orders of magnitude difference between the mass of the earth and the projected particle, you do not really sense the recoil velocity of the earth. Okay. So even for acceleration, whenever we consider acceleration, again from Newton's laws, it's the third law essentially. If you project something up, the mg should also be acting on the earth due to that particle that you have projected up. But we always see the motion of the particle and never sense that the earth is actually recoiling or having a gravitation such that we feel that staying on the surface of the earth. That's again due to the fact that acceleration is F over m. Even the F, the action reaction F, that's exerted to the particle, the same F is exerted on the earth as well. But if you divide that by m, the mass of the earth, the number will be very small. That's why you never sense, for almost all practical situations, you never have it. You need to have something which is compatible with the mass of the earth to sense that requirement. So this was just another example where actually the recoil is being sensed, but due to the fact that the mass being large, it's very small. Okay. Any questions here? Okay, so let's move on to another collision-like problem, and we'll take up collisions now. So everything till now had been in one dimension. The recoil or the ballistic pendulum essentially was a 1D problem. Now let's take up problems in two dimensions. The conservation of momentum problems in two dimensions. So we have the standard x and y axis here. And let's say a mass in A is traveling with a velocity va. Okay. And it's about to hit another mass in B, which is at rest, just begin with. This is at rest. After the collision has taken place, so this is after colliding, what happens is the two masses take off at different directions. So this is A, this is MA, and this is VA prime, and this is MB moving with VB prime. And this angle is given.
30.
Let's say we can also assign numbers here, but again, numbers are not. Maybe it's easier if I assign numbers. Let's say this is 30 degrees, and this angle is still unknown. This theta is unknown, and all we know is that the mass of MA and MB are given. Let's just assign some numbers. I mean, numbers are just to make things more practical, nothing else. So let's say this one is 1 kg and MB is let's say it's 1.5 kilograms, right? And let's say VA is 4 meters per second and VA prime is 2 meters per second. So our question is to answer what this angle theta is and what VB prime is. So I'll write down the questions here. VB prime and theta. Just to explain you the situation again. We have two masses, MA and MB to start with. And MA is about to hit MB with a velocity VA whose magnitude is 4 meters per second. MA and MB have masses which are 1 and 1.5 kilograms respectively. Okay. And MB is at rest to begin with. After the collision has taken place, these two guys fly off at different directions. A takes off at an angle of 30 degrees with respect to the positive x-axis, and the velocity magnitude being 2 meters per second. B takes off with VB prime. Okay. The primes, as you can see, are post collision. So whatever you see as primes, VA prime and VB prime, these are after. That's why I've just assigned prime. And with some angle theta. We are to find out what VB prime and theta is. So again, the same game, the conservation of momentum, but now in two dimensions. So effectively what you do is, you resolve each of the momentum along the x and y axis. So one dimensional problems we know how to do. Right? So always the plan is to resolve things into one. Even if you have a similar situation with three balls colliding, let's say, right? In space, not on a. This is more of an example of the billiard or the pool table. Two balls colliding, and you find out angles and so on. So this is more similar to that kind of a situation where the board is obviously a 2D surface. But imagine particles colliding in this room. Then also the x, y and z component velocities, if you resolve, and then the moment of conservation we apply along each of the dimensions. It's the same thing. Obviously, the calculation would be more involved. That's all. So we'll do the same thing here. We'll resolve each of the velocities and hence the momenta along the perpendicular y-axis and the x-axis. Okay. So to begin with, what is the total momentum here? Pi
MAVA plus.
is just Ma times V.
Yes.
This line was already at rest. I'm not putting in the numbers here. We'll do the calculation and then put the numbers. What is P? Let me call this as Pix. And there is no Piy. Piy, just for the sake of completeness, Piy is equal to 0.
0.
I stands for initial. And what is Pfx? Pfx would be the sum of the x component into this
VA
velocity
prime
and
cos
x
30.
component into
MAVA prime cos 30.
right. So MAVA prime cosine 30 added to MVDV prime cosine
theta.
which is still an unknown. Similarly, Pfy equal to MA VF prime
Sine
sine 30 minus a minus because this will have
Z.
a negative y projection. The y velocity, the VV prime velocity. Is that clear to all?
Yes.
So we'll think of a minus sign.
MBVB prime
VV prime
sine theta.
sine. So let me call this equation number 1 and let me call the second one equation number 2. Not yet. Maybe I can already apply the conservation of momentum and call those equations as 1 and 2. So as per the conservation of linear momentum, the x component should be conserved individually and the y
Y.
component. So Pix will have to be equal to Pfx. So for the x component, Pix equals Pfx. So which will imply that this MA times VA will be equal to MA VA prime
Cosine 30
plus MB VB prime cosine theta. Let's call this equation number 1. Similarly, for the y component, Piy will be equal to Pf y. That will tell you 0 will be equal to MA VA prime sine 30 minus MB VB prime sine theta. Call this equation number 2. See, you have two equations and two unknowns. All these MAs and VA and VA prime, these are all known. What are the two unknowns? VB prime and theta. So just in order to find out the theta, same as before, take the two equations and divide it.
Yes, sir.
You'll get a tangent theta. Take the arctangent or the tan inverse. Okay. In order to find out
1 by 4
magnitude,
minus
you square that. Then cosine square theta plus sine square theta would be 1. You get the magnitude. Okay. So the rest is for you to calculate. So this is just another example where in 2D you can actually find out the resultant unknown directions and the velocities. Now take this as another interesting homework problem to find out if additionally such a situation is elastic. You are told that so let me quickly define this equation here. So this is another problem which requires a bit of algebra to do along with trigonometry. So providing similar situation, very similar situation. MA and MB, and after collision has taken place, they take off in directions alpha and beta. This is this is again at rest, V is 0, and this has velocity V, and it's told that it's an elastic position. Now find out what alpha and beta are. Seconds. No, sorry. Find out what VA prime and VB prime are given alpha and beta. So the question is to find out VA prime and VB prime. Alpha and beta are given, these are known. I'll put a tick mark for the quantities that are known. So take that as a homework problem. And remember, it's an elastic position. So what does that tell you?
Kinetic energy.
Kinetic energy initially and finally are to be conserved. Apart from, moment of conservation is more basic. It will always hold, irrespective of elastic or inelastic or whatever position. Elasticity or elastic position is another additional constraint where kinetic energy is also. Okay, so having done that, let's move on to this problem of rocket propulsion. Sorry, I erased this. Are you done with it? Okay. So next we will discuss this example of rocket propulsion, and it's a very illuminating example in the sense that the rocket propulsion is one of the examples where the mass is actually changing with time. All these examples that we have been talking about for conservation of momentum or for the application of Newton's laws till now are the constant mass. Now for the rocket propulsion problem, because the fuel is burning by this combustion engine, the mass is actually changing. So the dp dt is, you cannot really pull out the mass outside the derivative and say that it's m times a. So this is a very illuminating problem in the sense that it involves second law application along with conservation of